We now look at the equations which govern the expansion of the universe. Strictly speaking, in order to do this, we need to employ Einstein's general theory of relativity. However, here we are mainly concerned with the results of such a theory and how it applies to cosmology. So what I will do in this talk, in this slide, is to give a derivation which is not a rigorously correct derivation, but nevertheless gives the results which the more rigorous Einstein's GTR gives. So I will call it a Newtonian pseudo derivation. Consider the universe to be made of a uniform sea of matter, and consider two test particles, rather two particles, one at its center, the center here, and another at this point. Now let us study the dynamics of this test particle with respect to this center. First of all, suppose this particle is moving away from the center at a velocity of dr by dt, r being the distance from this point to the test particle at any time t. Then the kinetic energy per unit mass for this test particle will be half dr by dt whole square. Let us now consider what is the potential energy for this particle. And here one should remember the following. Suppose I have a spherically symmetric distribution and I want to find the potential energy at a point inside the spherically symmetric distribution, then the portion of the distribution which will contribute to this potential energy, the gravitational potential energy, will be from that part of the sphere which is interior to this point. In other words, if I want to calculate the potential energy of this particle because of this sphere, the portion which is outside will be irrelevant and the entire contribution will come from here. So if rho is the density of matter in the universe at any time t, then the matter content inside the sphere is rho 4 pi r cubed by 3. And hence the gravitational potential for this test particle arising out of the sphere is minus g into the mass of the sphere divided by r. Now the sum total of these two things will be the total energy per unit mass for this test particle. We can now manipulate this equation into this form, and we can rewrite this energy E as dr by dt, that is the value of this energy today, as dr at half dr by dt whole square at today's epoch minus g 4 pi by 3 rho r square at t naught, which is today's epoch. There is overwhelming evidence that the total energy of such a particle per unit mass today is equal to 0. In the more rigorous language of general relativity, this will be called a spatially flat universe, but we will not go into the jargon for here. For our talk, it is enough to say that this E, which seems to play something like the total energy per unit mass of this particle, equal to 0. And hence we have that dr by dt divided by whole square divided by r square will be equal to 8 pi g rho r by 3 when this E is 0. Now this r can be distance between any two points. These are just two arbitrary points which we chose. Hence this equation for capital R will be true no matter which 2 points I choose in the universe. Hence, if a general distance scale I take in the universe to be A, then the equation which governs the expansion of the universe is dA by dt square by a square equal to 8 pi g by 3 times rho. Next. No, previous. Yeah, it's a different one. Okay. So now let us look at whether the universe is decelerating as it expands or accelerating. For this, let us do the following. Let us go back to the same picture in which we have this spherical portion defined by these 2 points, by this point and this test particle. Now, what is the force on this particle? As I said earlier, only the portion within the sphere will contribute and the portion outside will not for the gravitational field. So the gravitational force per unit mass for on this test particle is, you have rho into 4 pi by 3 times r cube, which is the total mass contained in the sphere. I multiply it by capital G, the gravitation constant, and divide it by the distance of this particle from this point, which is r square, and this is the total force per unit mass, that is acceleration, that is phased by this particle with respect to this center. And so I equate it to d2r by dt square, which is acceleration, and I simplify this and I can get twice d2r by dt square by r as minus 8 pi g by 3. Now here I need to mention an important point. This is true for non-relativistic matter, by which I mean the following, that only the rest mass of the particles of the matter inside contributes to the gravity. Suppose I have relativistic matter, that is the material here not only contributes the rest mass but is also moving so fast that because of relativistic speed, the increase in mass which results because of that, that also contributes to gravity. Then what happens? You know that random motion of particles of a fluid on a macroscopic scale manifests itself as pressure. In other words, if there is pressure, not only the rest mass of the particles of this fluid, but also the mass which results because of its relativistic motion also contributes. In other words, pressure has a dual character when you have relativistic particles. One is, it has this usual role of pushing things away. It has an additional role since it contributes to mass also from the E equal to mc square expression. It also contributes to an extra mass which tries to attract it by gravity. And so for relativistic matter, not only density but also the pressure will contribute to gravity, and this is the general equation we have for all matter.